that we haven't answered here, right? Which is, how do we find the best attribute? Everything depends on that if you think about it, right? Because if that procedure is good, then I'll get a great decision tree quickly. If that evaluation measure is bad, then this is all going to be a mess. Okay. So what might I use? What is a very let's not try to do something fancy. Actually, a lot of the time in machine learning, it's the simplest things that work best. Okay. So what would be a very simple criterion to pick the best attribute?
It evenly divides the training examples.
Evenly in terms of the number of training examples, or in terms of the number of examples of each class?
If for each training example you're going to be able to answer yes or no, if you pick the attribute that gives a more or less equal number of yeses and nos.
I agree with the first part of what you said. I'm not sure about the second, right? So here's the thing, right? Let's think about using just this attribute. Let's suppose that the decision tree was going to end here, right? I only got to use one attribute. Okay.
So it's either it should be more yeses or more nos, right?
Yeah, exactly. So let's suppose that in the beginning I have a training set where it's half spam and half not spam, right? The best thing that could happen to me is if I have one attribute that's perfectly separates spam from not spam. Let's say the presence of the word Viagra, right? I test whether this email contains the word Viagra or not. If it contains the word Viagra, they're all spam. If it doesn't contain the word Viagra, none of them are spam. This is actually not that far from reality. Right? There's obviously a little bit more to do, because that's why there's a lot of people who work on spam detection. But as a simple example, you get the idea, right? Now, most of the time that's not going to happen. But let's suppose that I have an attribute that when I split on it, on one side I get 90% yes, 10% no, and on the other side is 90% yes, 10% no, 90% no, 10% yes, versus one that's 60-40, right? Which one would you prefer?
90.
The one that gives you 90-10, right? Because at the end of the day, with that one, you're only going to make 10% errors, whereas with the other one, you're still making 40%. Okay. And since this is going to be a greedy procedure, right? Because we can't avoid exhaustive search. Probably what you should do is pick the attribute that looks best on its own. Okay. So this is a very simple idea, but it's a very reasonable thing to do. You just pick the attribute with the lowest error rate. Lowest error rate means that if I split on that attribute and then predict the majority class, how many errors I make. Okay? If I had 100 spams, I got 50 over here, 10 of them were not spam, and over there 10 of them were spam. So I got 10% or 20% of errors on each side. Well, that's my measure. Okay? So I just pick the attribute that has the best accuracy if you use it alone. Okay? And there's some details of how you do that here, but the idea should be fairly clear at this point. Okay. Now, how good is this? You can implement it and try it out, right? It's very easy, right? As part of your project, you can actually try this one out, and it's not terrible. It's certainly better than, say, random guessing. Even though even random guessing sometimes is not that bad if you combine it with good pruning, as we will talk about later. But anyway, this is not bad, but it's actually far from ideal. And let's see how this works, and let's see why it has some shortcomings. Okay. So here's a very simple training set. It has 8 examples: x1, x2, x3. They're Boolean. Okay. So let's evaluate each of these attributes. Okay. So let's take x1, right? So you see here x1, 0, 0, 0, 1, 1, 1, 1. Okay. So here's what happens for that example, right? Before I split, right, in my data set, how many positives and negatives do I have? 4 of each, right? Now, if I split on x1, right, what happens when x1 is 0? I have how many positive and how many negative?
3.
Right, 3 positive, 1 negative. Therefore, which one do I pick to as a prediction? Positive, right? Because then you'll be wrong what fraction of the time? 25%, right? So you get one wrong and 3 right. You agree? And on the other side, when x1 is true, what happens? How many positives versus negatives do you have? Now it's reversed, right? Now I have 3 negatives and 1 positive, so I predict negative. And I make 1 error. So total, I made 2 errors here. Okay? Now, if you do this for the other two, for x2 and x3, very nice, exercise. It's not going to stretch your brain, but you can do it, right? You get 4 errors in each. So not so great, right? So which one do you pick? x2, right? So notice that at this point we have a complete algorithm for learning decision trees. It's not going to be a great algorithm because mainly of the problem of overfitting that we will talk about later, but short of that, this is already actually not a bad algorithm in many ways. Okay? Now, here's the question though. Is this really the best we can do? Here's an example that shows why picking the most accurate attribute is not necessarily that great, right? I started out with a training set with 20 positive and 10 negative. And now I have this attribute x1 that creates the following split. And when it's true, I get 12 and 8. Okay, so how many errors? 8, right? And on this side, I get 8 and 2, so how many errors? 2, right? So what's my total number of errors? 10. And how many errors was I making up here? 10. So this attribute is no improvement, right? I might as well not bother. I basically have the same, mix of positive and negative that I had before. Okay? So by our accuracy evaluation measure, this attribute is not helping. However, let's say that we kept going. We just pick this attribute anyway because, we're, stubborn or something. And then we try x2. And then when we try x2, we get this. We get 12 and 0. And we get 0 and 8. Right? So after splitting on x1, splitting on x2 actually gives me 0 errors on this side. And on the other side, I get 8, 0, and 0, 2. Of course, this example is sort of like a little exaggerated, but you get the idea, right? We were actually making progress when we picked attribute 1. We just didn't know it. So the question for us is, what is going wrong here, right? And could we do something about it? Now, in general, right, we're not going to be able to solve this in all cases short of trying out all things, right? It's actually an NP-complete problem to find the smallest decision tree consistent with the data. So we're going to have to be heuristic. But the question for us is there a better heuristic than just the error rate? Okay. And of course, the answer is yes, or we wouldn't be talking about it. And that takes us into a little digression into information theory. Okay? How many people here are familiar with notions of entropy, information gain, information theory? Raise your hand if you are. Okay, very good. I didn't expect it to be, which is why we're going to do a flash introduction to information theory. Now, as a navigational warning, we're going to do this because we're going to introduce this other evaluation measure called information gain, or mutual information. And we need this very brief background on information theory in order to understand that. But at the end of the day, the information theory is really not going to be that important. We will see what it is that's important. People who use decision trees often get very fixated on the information theoretic aspects, and actually there's no need. The particulars of the information theoretic measure are actually not that important. Okay? Nevertheless, we do want to understand what it is, and why not learn some information theory in 5 minutes? Okay? So here we go. Let's suppose that we have a random variable. It's a Boolean variable. Think of it as flipping a coin, and the coin is biased. So you have some probability of the coin coming out heads. Let's say that is b equals 0, and some probability of it coming up tails. Let's say that is b equals 1. Okay, and the probability that v equals 0 is 0.2, and the probability that v equals 1 is 0.8. Okay, so the simplest distribution you can imagine. Right? This is called the Bernoulli distribution in statistics. 2 outcomes. Right. Now what we're going to define, and this is sort of like what Claude Shannon, when he invented information theory, which then took off like wildfire, this is sort of like what was his insight was, let us try to quantify how surprised you are when you find out the value of this variable. Okay? So I tell you, right? This is the distribution. Right? Another question is, if I tell you that it came out heads, how surprised are you? Right? If I tell you that the outcome was a 0, how surprised are you? And if I tell you that the outcome was a 1, how surprised are you? First of all, in which case are you more surprised?
When it's 0.
When it's 0, right? Because that's the less likely outcome. So first of all, our measure should have obviously a lower value, when the probability is lower, right? Makes sense, right? Number two, what if there's no uncertainty at all, right? Let's suppose that the probability of 1 is 1. It always comes out 1, right? What should the surprise be in that case? Well, 0, right? There's no surprise, right? On the other hand, here's a more exciting case, right? Let's suppose that, that the probability is 1 with 1, and 0 cannot happen, right? And then you see a 0. How surprised should you be in that case? Infinitely surprised, exactly. Like you're just infinitely surprised because that couldn't happen. Okay, so we want to measure that satisfies these desiderata. And now, what should it be? And so, what Shannon suggested was, let us make it minus the log of the probability. Very simple. There are many ways to justify this, but the intuitive one that I just gave you, I actually think is the best one. Right? This is why we have log. And we want it to be a smooth function, right? We don't want to be doing random things. It should increase smoothly with the probability and whatnot. But basically, what minus log of p does is it does exactly what we want. Okay? So if the probability was 0, it's infinity. If the probability was 1, it's 0, etc., etc. Okay? So this is the definition of surprise. Okay? Now, the reason this is important for communication systems and information theory and whatnot is that the more surprised you are, the more bits you need to send that thing if you're trying to be as efficient as possible, right? You should have the shorter bits for the things, you should have the shorter representations for the things that you're sending or recording more often, right? That's, the basic intuition, okay? For us, that is not really that important. What's important is, of course, the next thing, which is entropy, right? Even if you've never heard of information theory, you've probably heard of entropy because, the world is full of entropy, right? It's a popular metaphor, even outside of any technical field, right? So what is the entropy, right? The entropy is just the average surprise, nothing else. If I see outcomes of my coin flip and my coin has a particular bias, like say 0.2, 0.8, on average, how surprised I am, okay? So if you think, and this is often represented by the letter H. So H represents entropy, right? It's just going to be the sum over the possible outcomes, which in this case are just 2, but they could be 100 or 1,000,000, of minus the probability of that outcome times minus the log of the probability, right? Minus the log is the surprise. The probability is there because what? Why am I multiplying by the probability?
Taking the average.
Yeah, exactly. It's just the average, right? Things that occur more often should contribute more because I will be surprised by them more often. Okay? So the entropy is just the sum over all the outcomes of the probability of the outcome times minus the log of the probability. Okay? Very good. That was our flash introduction to information theory. Okay? It didn't take long. Okay? Now, if you're an electrical engineer, right, this stuff is really important to you, or even if you're trying to design, efficient compression schemes and whatnot. For machine learning purposes, however, here's the important thing about this, is that let us draw a graph of the entropy, right? Here's the graph. And in case you don't see this, here's 0, here's 1. This is the probability that V is equal to 0. And this is my entropy, H of V, right? And here's 1. And the graph looks like this, right? Let's look at this for just a second, right? What is the entropy when the probability of heads is 0? It's 0, right? You always get heads, and that's what you expected. Same thing when it's 1. Okay? But now let's look at where is the entropy maximum? Where do I get the maximum of the entropy? When am I most surprised on average?
Same probability on either side.
Exactly. When the probability is the same for both. When I have a fair coin. When I have a fair coin, I really have no idea what's going to come out, right? It could be either way. So I'm always as surprised as I could be, right? Notice that's what's happening here is a trade-off between something being probable, right? So P is high, and being improbable, so the surprise is high, okay? And so what we have, and the value of the entropy in that case is 1, right? And I will leave there, supposing that you're using logs base 2, okay? So it's 1 bit. I will leave it to you as an exercise to figure out why that should be the case, but you can probably see it already. Nevertheless, for our purposes, the important thing is that we have a curve with this shape. It's a smooth curve that starts at 0, gradually rises to an optimum, less and less and less as you go along, and then it's flat at just that point, and then it starts to get steep again. Okay? And in fact, if you took entropy and replaced it by some other function that looks the same, you would probably get about the same results. In fact, people in computer science like to use entropy because of information theory and whatnot. But people in stats often use this other thing called the Gini coefficient, which has nothing to do with information theory. It just has a shape that's very similar. And empirically, information gain tends to work better than Gini, which is why we're covering it here. But it's not a big deal. The big deal is that the shape of the curve be this. Any questions so far? Okay, so the question is, sure, I'm telling you this, but why should you believe me, right? Why is this shape of the curve important? And why is it that having a curve like this helps us do better than just picking the attribute with the lowest error? Okay, that's the key question. Oh, sorry, actually, before we go on to that, what we typically use is not just the entropy, but what is called the mutual information. Right? What is mutual information? It's the mutual information between two variables is the reduction in the entropy of one of the variables that you get from knowing the other. Okay? In particular, we're going to be interested in the reduction in the entropy of the class that we're going to get from knowing the value of a particular attribute. Okay? So the attribute with greatest mutual information with respect to the class, or the attribute with the greatest information gain, is going to be the one that we pick. Okay? Because it's the one that most reduces the uncertainty about the class. In particular, if our attribute reduces the uncertainty to 0, then it has the maximum possible information gain, and we can pick that. Okay? So more precisely, what is the mutual information between two variables a and b, denoted by the letter I? It's the entropy, actually, there's a typo here, the entropy of a. This actually works both ways, right? So it's the entropy of pick one of the variables, it's symmetric, let's say a. It's the entropy of a minus the entropy of a after you know b. And again, this has to be averaged by how often different values of b occur. So this is going to be the sum over the values of b of the probability with which that value comes up times the entropy of a conditioned on b. Right? If I select only the cases where b has that value, now what is the entropy of a? Okay? So to compute the information gain, I need my entropy before I split on the attribute and my entropy in each of the branches. Okay? And then I average those entropies, weighted by how many examples went in each direction, and the difference between the two is my information gain. Notice that actually, if you didn't want to bother with h of a, you don't have to, right? Why is that? Well, what I'm saying is that even though this is the definition of mutual information, if I just took this out and considered only the entropy of a given b, I would be okay.
Well, just because aren't you choosing like the min or the max?
Yes, but
And
No,
since that term is in all of those,
precisely.
it cancels out.
Exactly. I am not precisely. I am not interested in the particular value. I'm only interested in picking the one that has the maximum value. And this contribution is equally there for all of them, right? The entropy of A is independent of the attribute that I'm testing, so it's going to be the same for all. It's going to affect the exact value, but it's not going to affect who comes out on top. Okay? So if you actually look at the code of decision tree learners, they actually don't bother with that part. But it's good to understand that effectively what we're computing is the mutual information. Okay? And now you know how to compute it. For example, you could apply this to the example that we saw before. Right? So here's my initial training set with 20 and 10 examples, 20 positive, 10 negative. Here's my initial entropy. And then, here's my entropy after I split on x1 equals 1. And this is for x1 equals 0, right? I have given these values, I can compute my probability and therefore my entropy, right? I also know that 2/3 of the example go this way and 1/3 go this way. So I have all the information that I need, right? It's this here minus this times this plus this times this gives me this value. And lo and behold, it's greater than 0. This is the important thing. Remember, for accuracy, the difference between the error rate before and after was 0. I was making 10 errors before, I was making 10 errors after, so my gain was 0. But here my gain is not 0, my gain is positive. So error rate couldn't tell that we were making progress, but information gain can tell that we're making progress. Okay? So now that's the case in this example, but why would this be the case in general? Okay, that's the next question for us, right? Does this happen in general, or did we just get lucky this time? In fact, it happens in general, at least it happens in a very broad number of cases. There are cases where we're making progress where information gain also can tell, and we'll see one in a little bit. But there are many cases where it can detect progress where error rate wouldn't. Okay? So now let's see why that is the case. Okay. So here's my my probability of the class, spam or not spam or whatever, right? Here I have from 0.5 to 1 because I've kind of zoomed in, and here I have from 0 to 1, right? So this is the absolute error, right? And here's what the curve of the absolute error looks like, right? It starts at 0, right? Obviously, if everything is of one class, there's no error. And then it's a straight line, right? Because it just goes up proportionally to the probability, right? Until it gets to 0.5, right? And then it flips because now the other class is in the majority, so now I start predicting the other class, so now as the probability increases, my error rate starts to go up again, okay? Or my accuracy, you know, my, depending on how I look at it, right? Either the error rate is going down or the accuracy is going up, okay? So I have my biggest error here in the middle when it's 0.5, 0.5, just like entropy, right? When it's as good as a coin flip, right? And it goes down to 0 on both sides. So this is very similar to entropy, right? The big difference is that this here is a straight line, and in the entropy, if you recall, what I have is a curve like this, right? Why is the curve better than the straight line? Let's zoom in on this curve and see what happens, right? So here I've zoomed in on one part of this, right? And let's, you know, here are two values of the entropy, 0.6 and 0.8, right? And let me draw the arc between these 2 points. Now here's the thing is that in the beginning, right, before I split on the attribute, I was somewhere in here. Like I had, let's say, on my whole data set, my probability was 0.7, let's say, right? And therefore my entropy is, you know, close to 0.9, let's say. Okay? The exact values obviously don't matter, right? And now what happened is that I split my data set into two, right? In one of those data sets, the probability of the class has gone up, right? And in the other one, it's gone down, right? I concentrated the spams on this side and the non-spams on that side, okay? So now what I have is two data sets with two values of the probability, and therefore two values of the entropy. One is higher, right? And the other one is lower, okay? Everyone with me on this page, we start out in the middle. When we split, we get one lower and one higher, okay? And now, my new entropy, right, is going to be the average of those, right? And the average of those is going to lie on this straight line. Where exactly it's going to lie on the straight line depends on what fraction of the examples went one way and the other, right? If it was 50-50, I would have to pick this point here in the middle. If it was, you know, 1/3, you know, 2/3, it would be somewhere over here, right? But here's the key point, is that irrespective of where that split actually happens, this line is always below this line. The line of the entropy is always above the line of the average of the entropies. The technical term for this is that the entropy is a concave function. Okay? And conversely, the mixture information is a convex function. Sometimes people abuse and just call concave and convex convex. Right? But that's the key, is that the line is always below the curve. Here, right, the error and my measure are actually, you know, always on top of each other, and so I can't detect the progress. In this case, I can detect the progress. And now you also see why the details of the entropy don't really matter. The Gini coefficient has the same, you know, shape, and therefore also works. Okay? Questions? I know this was a little bit of a, you know, quick sequence of things. It's good to sit down with this after class and go through it again, but hopefully at this point you at least have the gist of the idea. Okay? So any questions before we continue? Okay, very good. Let's see how we're doing on time. We're doing pretty good on time.